Now that we know how to solve both systems of equations and systems of inequalities, we can look at this idea of linear programming. The idea of linear programming is we want to maximize or minimize something given some given constraints. We're going to have our objective function, which is what it is that we're trying to maximize or minimize, and our constraints, which is going to be a sequence of inequalities that are restricting our objective function. The first step in linear programming is to graph your system of inequalities. We then determine the vertices of the region defined by our system of inequalities. If our maximum or minimum exists, it will occur at one of the vertices. So we need to determine these vertices, and our maximum and minimum will happen at one of those. So we will then plug those vertices into our objective function to determine our maximum or minimum depending on what we need for the problem. Let's look at maximizing z equal to 2x plus y. And our constraints are x greater than or equal to 0, y greater than or equal to 0, x plus 2y is less than or equal to 5, and x minus y is less than or equal to 2. The fact that x and y are greater than or equal to 0 just tells me I'm in this first quadrant. I'm only going to be dealing with positive values. So I'm going to start with this x plus 2y less than or equal to 5. Subtracting x from both sides gives me 2y equal to negative x plus 5. And then we can divide by 2 to get negative 1/2 x plus 5 over 2. We can see that if x is equal to 1, then y would be equal to 4 over 2, or 2. In addition, my slope here is minus 1/2. So as I go down 1, I should be going over 2. And I can continue that process. This is a less than or equal to, so I will be using a solid line. And since I want y to be less than, I want smaller y values, so I need to shade below it. My other equation says x minus y is less than or equal to 2. I can subtract x from both sides and multiply through by negative 1 to get y is greater than or equal to x minus 2. This tells me that my y-intercept is negative 2 and my slope is 1. And once again, I'm greater than or equal to, so I should be able to use a solid line. This time, I want y greater than or equal to, so I want to shade above. So I need to be below the blue line and above the red line, and I do need to be positive. I now have 4 vertices. One here, one here, one here, and one here. This one down here is probably the easiest. It's 0, 0. This one right here, this is the y-intercept of the blue line. So in this case, x is 0, y is 5 over 2. This is the x-intercept of the red line. In this case, y is 0 and x is 2. And then we have this point here. We can look at this graph and probably figure out that this is 3, 1, but maybe if we didn't have such an exact graph, it might be a little bit hard. So another way to solve this is to take these two equations, x plus 2y equal to 5 and x minus y equal to 2, and solve this system. I'm going to multiply this second one by negative 1 to get negative x plus y equal to minus 2 and add them together. That gives me 3y equal to 3. Dividing by 3 gives me y equal to 1. I can then plug that in. I know x minus y is equal to 2. Adding 1 to both sides gives me x equal to 3. So I do get that point 3, 1. Now that I've found my points, I just need to plug them into that objective function. If x is 0 and y equals 0, I have 2 times 0 plus 0, that's 0. 2 times 0 is 0, plus 5 over 2 is 5 over 2. 2 times 2 is 4, plus 0 is 4. And 3 times 2 is 6, plus 1 is 7. So I can see that this is my maximum. So in this case, I have a maximum of 7 that occurs at the point 3, 1. I now want to maximize 2x plus 3y, and my constraints are x greater than or equal to 0, y greater than or equal to 0, 2x plus y less than or equal to 8, and 2x plus 3y less than or equal to 12. Once again, the first two just tell me that I'm only dealing in the first quadrant, that everything has to be positive. My next equation, 2x plus y less than or equal to 8, I'm going to do this using intercepts. If x is 0, this equation turns into y equal to 8. So we can plot that point 2, 4, 6, 8 up. And if y is equal to 0, this becomes 2x equal to 8, or x is equal to 4. And then we can then connect those dots to get the line and its graph. This doesn't help me with my shading. I will have to go ahead and use a test point here. Using 0, 0, 0 plus 0 is in fact less than or equal to 8, so I'm going to shade below this line. My next line, 2x plus 3y less than or equal to 12. If I let y be equal to 0, I have 2x equal to 12, or x is equal to 6. If I let x be equal to 0, I have 3y equal to 12, or y is equal to 4. And then I can connect those dots. Once again, picking a test point like 0, 0. 0 plus 0 is in fact less than or equal to 12. So I have this shading that's below the red and below the blue, and also still positive. I have 4 test points. I have the point 0, 0. We've already found this point to be 0, 4. And this point to be 4, 0. So now I just need to identify this point. So I have the system 2x plus y equal to 8, and 2x plus 3y equal to 12. I'm going to multiply the first one by -1 to make it minus 2x minus y equal to minus 8. That gives me 2y equal to 4. Dividing by 2 gives me that y is equal to 2. Substituting back into the first equation, I have 2x plus 2 is equal to 8. I can subtract 2 from both sides to get 2x equal to 6. And divide by 3 to get x is equal to 3. So this is the point 3, 2. We then need to plug each of these points into my function, my objective function, to figure out which one's the maximum. 2 times 0 plus 3 times 0 is 0. 2 times 4 is 8. 3 times 0 is 0. And 8 plus 0 is 8. 0 times 2 is 0. And 3 times 4 is 12. So this one would be 12. 2 times 3 is 6. And 2 times 3 is 6. So 6 plus 6 is equal to 12. So we actually have a range of values that work for our maximum here, but we can definitely say that the maximum is 12.